Random variables and probability. Think back to when you started learning about probability. Remember finding the probability of flipping a coin? Well, let's break down that activity further. A probability model describes all of the possible outcomes of a chance process, like flipping a coin. For example, if a coin is tossed twice, the probability model would consist of 4 equally possible outcomes. You could get heads and heads, heads and tails and heads, or tails and tails. If we define the variable capital X as the number of heads resulting from the tosses, there are 3 possible values, 0, 1, or 2. The likelihood that capital X is any one of those values can be found by grouping each possible outcome according to the number of heads that are found. So if the number of heads, or capital X, is equal to 0, the only outcome that fulfills that is tails, tails. If capital X, or the number of heads, is equal to 1, there are 2 possible outcomes that fulfill it. You could have heads, tails, or you could have tails, heads. And if capital X, or the number of heads, is equal to 2, the only outcome that satisfies that is heads, heads. Each outcome has a quarter probability occurring. So X equals 0, or capital X equals 0 and capital X is equal to 2, both have, or each have, a 1/4 probability, while capital X is equal to 1 has 2/4 or 1/2 probability. And what we have with these outcomes and their probabilities is called probability distribution. The variable capital X in the coin toss example is a chance process, meaning that the outcome is random. When a variable describes a numerical value of a chance process, it is called a random variable. The probability distribution of a random variable gives its possible values and probabilities. What if we wanted to find the mean of the probability distribution from this last example, where we have the values of X being 0, 1, and 2, and the probability of each one being 1/4, 1/2, and 1/4, respectively? Well, the mean, or X bar, is the average of a data set. However, the mean of a random variable is slightly different because we need to account for some values of capital X to be more likely than others. The mean of a random variable capital X is the sum of the products of each possible value and its probability. This mean is represented by the Greek letter mu, and that's how it's pronounced, mu. So mu with capital X and subscript is equal to the summation of capital X within that position with I and subscript times the probability of that value. So in our example, we have that mu sub X is equal to our first random variable X was 0 and its probability was 1/4, plus our second random variable value, which was 1, times its probability 1/2, plus the random variable value for our third option, which was 2, times its probability 1/4. So we would have 0 plus 1/2 plus another half, which is equal to 1. So that's what the mean of the random variable capital X, or mu sub X, is equal to. The mean is the center of measure of random variables. Therefore, the next step is finding the measure of spread using standard deviation. Recall that a sample standard deviation is denoted by lowercase s, and when squared, in other words, s squared, it represents what is called the sample variance. The standard deviation of a random variable is denoted by lowercase sigma with capital X and subscript, and it's found by sigma, capital X and subscript, is equal to the square root of the summation of capital X sub I minus mu sub capital X squared times the probability of each item. The variance of a random variable, or lowercase sigma with x in subscript squared, is the part under the radical that is the average of the squared deviation of the values of the variable from its mean. So lowercase sigma with capital X in subscript squared is equal to the summation of capital X sub I minus mu subscript capital X quantity squared, and then times the probability of each outcome. In other words, if we take our original equation and we square both sides, we get that lowercase sigma with x in subscript squared, and the radical goes away. Random variables generally come in two forms, discrete and continuous, and there is a big difference between them. Discrete random variables are random variables that take on distinct separate values. These values are generally countable. So an example would be set B as the outcomes when rolling a six-sided die. The outcomes are the numbers 1, 2, 3, 4, 5, and 6. They are distinct. You can't have anything else except these 6 outcomes. Whereas continuous random variables are random variables that can take on any value within a range or an interval. And these values are generally infinite. In other words, they're not countable. So an event C could be the numbers contained in the set of integers. Well, integers are both negative and positive numbers, including 0, but there are no decimals in between. So you would have like -3, -2, -1, 0, 1, 2, 3, and so on. And it continues in both directions, both the positive and negative. And because there is no ending value here and they just continue on, it makes it a continuous random variable. Let's go over a few examples of discrete versus continuous random variables. Here's our first one. The random variable r is defined as r is equal to 1 if it's raining outside, or 0 if it's not raining outside. Is r considered to be discrete or continuous? Explain. Well, if we look at our random variable r, it only has these 2 contained values, and they are within conditions that are distinct or separate. So this is going to be discrete because, again, the outcomes are distinct and separate values, and one can count the number of values that a variable can have or represent. There are only 2 of them. It's either 1 or it's 0. So that's what makes this one discrete. Let's look at another example. The random variable t is defined as the exact amount of time it takes for any object to fall to the ground. Is this one considered to be discrete or continuous? Explain. Well, since the amount of time that it takes an object to fall to the ground isn't always clear and distinct, like it depends on where the object is dropped from and what the object's mass is. So because the amount of time can vary here, it's going to end up being continuous. It could be anything. It could be a feather, it could be a book, it could be a spoon. And therefore, there are an infinite amount of values that the variable can be assigned. Now let's talk about the mean of a discrete random variable. It is a weighted average of the possible values that a random variable can take. In past courses, we have been calculating the sample mean of a group of observations, where each observation has an equal weight. Instead of observations having equal weight, though, the mean of a random variable weighs each outcome according to its probability, or mu, which is the Greek letter that we use for the mean, is equal to x sub 1, or the weight for the first event, times the probability of that first event, plus the weight of the second event times the probability of the second event, plus dot, 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 plus the weight of the nth outcome times the probability of the nth outcome. In sigma notation, it's written as sigma, where k is equal from 1 to n, of x sub k times p sub k, where x sub k is the weight of each outcome and p sub k is the probability of each outcome. Let's try an example. Avani is playing a gambling game where it is possible to lose $2, break even, win $4, or win $6 each time she plays. The probability distribution for each outcome is provided in the table below. What is the mean for this game? Well, we know that the mean, denoted by the Greek letter mu, is equal to x sub 1 times the probability of that event happening. So this is the outcome times the probability, plus x sub 2 times p sub 2, plus x sub 3 times p sub 3, plus x sub 4 times p sub 4, since we have 4 outcomes going on here. So in our case, outcome 1 is that you lose $2, and the probability of event 1 happening or outcome 1 happening is 0.5, which is 1/2, or 50%, plus the payoff for the second event, or the outcome for the second event, which is 0, and we're going to multiply by its probability, which is 3/10, or 30%, plus outcome 3, which is 4, times the probability of event 3, which is 15%, or 15/100ths, plus the outcome number 4, which is 6, times the probability of outcome 4 happening, which is 0.05, or 5%. Now let's evaluate. -2 times 5/10, or -2 times 1/2, is -1, plus 0, plus 6/10, plus 3/10. And if we evaluate this, we'll get -1 plus 0.6 will be at -0.4, plus 0.3 would be at -0.1. And since our outcomes are in terms of money, that would end up being written as -10 cents. That is the mean for this game. And here we have the solution to this problem, and it does match the solution that we calculated, that the mean, or mu, is equal to x sub 1, or the outcome, times the probability of event 1, which is p sub 1, plus x sub 2 times p sub 2, plus x sub 3 times p sub 3, plus x sub 4 times p sub 4. And again, we multiplied each outcome by its respectable probability and added them up. And we did end up getting -1/10 of a dollar, or -10 cents, for our mean.